Okay, good morning everyone. So we're going to continue our lecture this morning with the derivation of disk masses, which is obviously a very fundamental property of a protoplanetary disk. But unfortunately, it's still really hard to determine its mass observationally. As an introduction, I'll start with the so-called dust mass budget problem. Basically, the dust masses that we measure appear to be really low compared to what we need for exoplanets. And then I'll go over essentially how do we calculate the dust mass and what are all the uncertainties therein, including somebody has transferred that. I'm going to do on the whiteboard because I feel that's easier to follow along. So just bear with me at that point. I'll switch on the light when I get to it. And then the second part of the lecture, I will talk about the gas mass, which is even more uncertain and even harder to derive. But also there, we're starting to make progress. So, again, let's recall our structure of gas mass in a protoplanetary disk, where we have the millimeter dust material really much smaller than the gas disk. And remember that I think this is the consequence of dust evolution, and most importantly, the radial drift. The millimeter dust particles will drift inwards, and therefore that the dust is in fact not a very good tracer of the disk mass because of this evolution by both growth and drift. This is particularly true if we look at some dust evolution models. Where we see that for a disk that has no pressure modes, the unpure density profile, that the dust mass initially builds up just by the growth of the dust grains, but then at 1 million years the dust mass will actually very quickly go down because of dust falling onto the star. And this is not true in the case of a disk that has dust traps, but at the moment we there seems to be quite a lot of evidence that many disks are affected by radial drift. So this is just something to keep in mind. However, if we just consider the dust mass for now, there is people have thought about this for quite a long time. Like, what is the amount of solid that you need in order to form a planetary system? And initially that was the solar system. 70s, 80s, those were the only planets that we knew. And obviously for the solar system, we cannot go back in time and measure the disk mass, but there were already some estimates back then, which were not that original. There's a lot of the protoplanetary disk methods that we use are still kind of based on this. And this is the so-called minimum mass solar nebula. So what you do in this case is that you take each planet, you measure its solid mass. So for the gas giants, you only take the core mass, and then you multiply by the solar composition. So you have to kind of correct for the fact that planets have a different composition than the sun. But we assume that everything originated from the same composition. So then we have a mass for each sort of planet location. Now, of course, we know that each planet has a radius, and we can divide the solar system into annuli, like with different widths, so that each annulus contains one planet. And then that planet, or the mass of that planet, can be divided by the area of that ring, and that will give you a gas surface density. So based on that, they essentially derive this gas surface density profile. It actually followed a very nice power law. And then you want to kind of go back to recalculating the solid surface density, and they do that assuming that something happens high at the watershed line. And remember, this is because of the idea that solids outside of the water snow line are more icy, more sticky. This happens to be the location of Jupiter. So therefore, the idea is that the solid content was also larger outside the water snow line than inside the water snow line. you essentially end up with these numbers. So that's the same profile here, and a total gas disk mass, minimum disk mass required to form the solar system of about 1% of the mass of the sun. And so in basically before ALMA, there were of course some measurements already of disk masses. These were only the bright disks, but still, these were some estimates that we had. And it turned out that these disks were actually quite similar to this minimum mass solar nebula, with within a number of us. But again, there was this bias here towards the brightest disk that could be detected at that time. Okay, so now that we have many more observations about the planetary disk, we can start to look at this statistically and also start to do a comparison with exoplanets. And Marel et al. Found that there was some restraints going on here. This is the dust mass on the vertical axis. So this is either the dust mass in a disk or what we call the solid mass in an exoplanet as a function of stellar mass. And what we found is all the red data points are disks and all the green data points are exoplanets. And the blue shaded region is then kind of the computed statistical average of an exoplanet. So without going into that whole computation, what you can see is that the typical core mass of exoplanets is higher than the dust mass in the disk. So, and remember, we're using this term protoplanetary disk that essentially says like whatever is in the disk will become an exoplanet. But that's not possible if your dust mass budget is already lower than the exoplanet mass to begin with. So this is already suggesting that either our dust mass calculation is wrong, or we are underestimating, or exoplanets are already formed at the time that we're observing the protoplanetary disks. And so this was a follow-up study where we looked at essentially the dust masses, now not just of class 2 disks, or class 2 protoplanetary disks, but also of class 0 and class 1 disks. So the dust masses of those disks are 1 or 2 orders of magnitude higher, and those are indeed, of course, much more similar to the disk mass of exoplanets. However, there was some issue with this calculation here. That was so this is another paper that followed kind of in the series from another author, and he said, yeah, you cannot just take all the exoplanets from your exoplanet catalog and use that as your typical exoplanet solid mass, because there are both selection biases and detection biases in that sample, which you need to correct for. So the idea was, first of all, to correct for the selection bias, which is, so in exoplanet studies, most stars that people choose to look for exoplanets are solar type stars, because that was always our interest. Can we find planets around stars similar to our sun? If you correct for that, for example, in this survey, this is what your exoplanet diagram looks like. You see it becomes very different than this diagram. And then second, you need to consider the detection bias. So you shouldn't just look at what you have detected, but also for what you have not detected, to really say something about how common certain exoplanets are. So if you so this is what they show in this problem. This is the actual occurrence of different types of planets. So that means that if you look at the exoplanet solid mass distribution, this was this is the mass distribution, the cumulative mass distribution, originally just using the catalog. And then if you correct for selection and detection bias, you actually get something like this. You see that the planet mass, the real planet masses are actually a lot lower. And then there was a second part, that in the protoplanetary disks, there is actually an opposite selection bias. Again, related to the stellar masses. Because if you remember that from the IMF is is peaking for low mass stars, sort of 0.2 solar mass stars. So you only want to look at the stars that are closer to solar, so that you essentially have a maximize the opposite way. If you get rid of all those low mass stars, and now you actually have like dust mass and exoplanet mass distributions that you can compare with each other. And then you can distinguish between Kepler planets and radial velocity planets, so the different techniques, but they are all quite similar. And so the conclusion of this paper is that the dust mass budget, there's still a problem because the dust masses in protoplanetary disks are similar to the dust mass in exoplanets. And so that would imply that all the dust mass that is there has to be converted into planets. And essentially, planet formation models don't predict that. They say that only part of the solid material will be transferred to planets. But at least it's not as pessimistic as those earlier papers. So if you're interested in this, then make sure to use the proper statistical method. Okay, so then so we still have a problem with the dust masses in protoplanetary disks, that they seem to be too low. Other than the possibility that exoplanets may form early, we can also assume, well, maybe there's something wrong with our dust mass calculation. So I'm going to go through some radiative transfer to show you how we actually do this. So the flux density that we measure is this is given in density. Is essentially the integration over the specific intensity, so whatever your disk emits, integrated over the emitting area. And the specific intensity, so how much does dust radiate, that's not too complicated function. It's actually the black body function, or the Planck function that we know, multiplied by 1 minus e to the minus tau. So this is to correct for optical depth effect. The tau is essentially the optical depth. The Planck function we've seen before, it looks like this. And the optical depth itself can actually be expressed by the dust opacity. So this is depending on your dust properties, you get a certain value, and the sigma dust, so the surface density of your dust. And you can then divide that by cosine I to correct for orientation effects, but for simplicity, we're going to just leave out that term in the following calculation. So the dust opacity, I already mentioned, this is something that's related to the composition, it's related to the size distribution, so n of A, where A is the size of the dust grain, so you always have a number of different sizes with a power law key, minimum size, maximum size. And yeah, there's this paper by Drayton 2006 where he does a bunch of calculations showing that this is how kappa changes depending on your assumed grain size distribution. Okay, so kappa is essentially something that we can assume, we can take from a catalog, or we can take from some calculation of grain size. We're mostly going to focus on the math here of the radiative transfer. And for the dust temperature, so this dust temperature generally depends on the infalling stellar radiation. And there's this expression for a passively heated flared disk, you radiate at equilibrium. The derivation is in this paper. I'm not going to go through that because that's there's a lot of geometry and dust absorbing radiation, emitting it down, scattering, etc. But the general expression is something that just depends on the stellar luminosity, the flaring angle, that's phi here, a couple of constants, and r squared. So r is the distance from the star. So the whole thing depends on the square root over r. The further away you are from the star, the lower your temperature. And then in calculating the total dust mass, what you often see is that people assume a constant temperature. So they don't actually take like a temperature profile over the entire disk. they usually assume 20 Kelvin, or maybe 10 Kelvin for a low mass star. And that may sound a little crazy because we have that temperature expression. So there is definitely a temperature dependence, and we can see that here in this plot. So this is the temperature as function of radius calculated this equation for 3 times of luminosity. But as you can see, the steep temperature gradient is only at small radii. And if we assume a disk that is like 50 to 100 AU in size, the bulk of the material is in that low temperature regime. So it is actually quite reasonable to take a constant temperature because the bulk of the mass is located in that low temperature. So that's why you can often make that assumption as well. Okay, so how do we compute this mass? And I've written this out because I was sure it was going to go wrong if I did it by heart. I don't know if you guys have that experience. This is my some memories from when I was a student. That the professor starts writing things on the board and halfway said, "Shit, I did something wrong." So I'm just going to copy it from okay. So in our calculation, remember what we want to calculate is the dust mass, and we're going to assume that the emission is already thin. And I'll show later, if you don't make that assumption, then it becomes, it's essentially impossible to calculate. So we're going to make the assumption that the emission is already thin. So we have our dust mass, that is, okay, can you see this? Yeah. It's an integral sigma r to p 2 pi r dr. We have our expression of the surface density, so a power law of the surface density that we can plug in here. So now we have sigma c r over rc to the power minus 1 times 2 pi r dr. So that's still the same, right? So now what we see, we have an r here to the power minus 1, we have an r, so we can strike those out. And that means that we're left with sigma c 1 over rc to the power minus 1, so that essentially becomes rc itself. And we have our 2 pi, and we have a dr. And as you can see, so we're integrating over r here, but there's no more r in this equation. So essentially, these are all constants now, and we just integrate over the entire disk, so from 0 to r out. And yeah, if you have something like integrating over the r, that is just r between 0 and r out equals r out. So, yeah, this is not too fast, I hope. You've done integral.
This is very fast. This is straight.
I feel this is really straightforward, but I don't want to.
But this is great, but you don't get one in sigma c.
Sigma c. Oh, so this is the that is the expression that we use for the surface density. So we assume that the surface density is the power law, multiply it by a constant sigma c. So just a scaling constant. Yeah. No problem. And that's that's why you should ask questions. Don't get confused. Okay, so then we're left with our expression for n dust, 2 pi sigma c rc times r out. Right. Okay. So now we have our expression for n dust, and now we want to understand how we can relate the flux to the n dust parameter. So we have f mu is the integral over I mu delta omega. Our delta omega is just the emitting surface of our disk, right? So that's again 2 pi r dr divided by the distance squared. That's our And our I mu, we had already defined here. That is the Planck function times that 1 to the minus e tau. But we're taking an optically thin assumption. So we're taking tau mu is much smaller than 1. And that means that 1 to the minus e minus tau is actually going to approach tau itself. And the reason for that is actually that if you have, in general, e to the x can be expanded into a Taylor series. 1 plus x squared over 2 plus x third, 3, etc., etc. And so it means that if x is small, all of these terms disappear, and then ex is essentially 1 plus x. And that means that the expression here, so 1 minus is going to become low here. So this whole thing becomes 1 minus x, and that means that it becomes x. So this whole expression becomes equal to tau for a low value. That makes it a lot simpler. So now we have I mu is b mu, which is a function of t, and times I. And then multiplied by 2 pi r over d squared dr. So now we have this as our expression. We also have this expression. Tau is essentially equal to the dust capacity times the surface density. So we're going to fill that in as well. Tau, kappa, sigma, r, 2 pi r, d squared r, and then we're going to fill that in as well. So this is really just filling in things that we already had this now before. Sigma c times r, rc minus 1, 2 pi r, d squared dr. Yeah, that means we can cross out that r, again, this r against that r again, and we are now left with b mu to c kappa sigma c rc, making sure I don't forget anything, 2 pi d squared dr. So again, we have an integral over constants and dr. We again integrate over the entire disk. So we are left with b mu of temperature, kappa, I'm going to move the distance here now, sigma c, rc, are 2 pi r out. Okay? This expression is the same as n dust. So that means that we're left with b mu of temperature, kappa, n dust divided by t squared. And yeah, that's it. This is how we calculate the dust mass. It comes from going through the math of this with a couple of assumptions. And this is the final equation. And I showed this equation yesterday also on my slides, but now you know where it comes from. So in the assumption that the dust is optically thin, we can express the flux as a function of dust mass. And of course you can reverse the terms and you can calculate the dust mass from the flux. And then this is Planck function. Like I said, we normally use a single temperature, 20 Kelvin, so that means that also this thing becomes a single value in the whole equation. And all of it, so the whole thing just depends on the distance and the flux and the dust mass. So the dust capacity can be calculated using something that's called knee theory. There are many dust capacity tables also available online. I'll give a link for that later. And so generally, to compute the dust mass, we use this equation. So we use an integrated flux to compute the entire dust mass. If you want to do something more fancy, you can essentially do full radiative transfer, where you actually take into account that there's a surface density and a temperature dependence. There are tools for this, like radiative transfer tools, to do this whole calculation, like for a given surface density profile. Yeah, this is by far the most common method because it's very simple. Yeah, that's basically it. Then we have one other approximation. Oh, actually, I'm just on the left. Sorry, I'll leave this up. I'll go to the board. So we have one other approximation to make things simpler. That is, if we don't want to do that full Planck function, we can also make an approximation here where h nu is much smaller than kt, which is kind of valid in a millimeter regime of your density. And that means that the Planck function is now going to get a very simple expression as well. So let me write that up into 2. So V nu T equals 2h nu third C squared 1 EH nu AT minus 1. So we're making this approximation. So again, we have this x being very small in e to the x. So this thing just becomes equal to 1 plus x. So this becomes 1 plus h nu at minus 1 times 2h nu third c squared. And 1 minus 1 goes away, and this expression becomes kt h nu 2h nu 3 c squared, right? And that means that we can cross one of these, and we are left with 2 nu squared kt c squared, and that's it. Now we have a much simpler expression of the Planck function. And let's see if I did it correctly. Here we go. So now we have the Planck function as an expression of new frequency and temperature. And kind of the key thing here is that the Planck function is now, in this relativity approximation, the Planck function is proportional to the frequency squared. And you remember that I said that the dust capacity is proportional to nu to the power beta. And this is then how the whole thing comes together. So in the radiant genes and also the thin regime, which is generally what we assume means wavelength, the flux is proportional, can be seen as this expression. That means that the flux is proportional to nu squared from B and times kappa. And kappa is nu to the power beta, so that means nu 2 plus beta. And The flux itself can be expressed as mu to the power alpha, where alpha is the measurement of the spectral slope. This is an observational quantity, this alpha. And within this regime, we can say that alpha equals 2 plus beta. So essentially the spectral slope becomes related to the dust opacity, the dust grain size distribution. And this is why you will often see in literature spectral index measurements of protoplanetary disks. Like they measure the spectral slope between two fluxes to relate that back to the grain size composition and the grain size itself. But as you can see, it relies on a number of assumptions, which they're not totally invalid, but we have to be a little careful. Okay, so that's it for the equations. Like I said, I'll leave this in the boards. Want to copy it later. So a few more examples of the dust opacity. So here are some dust opacity tables that people have computed. For example, here we see like dust opacity of large grains versus that of small grains. And here we can see, in fact, that the dust opacity of large grains becomes dominant in the millimeter regime. So this is kind of where the idea, the reason comes from, that at millimeter wavelengths you're sensitive to larger grains. It's because the dust opacity there is dominated by the large grain opacity rather than the small grain opacity. And then there's also like the beta itself depends on the composition and on the grain size. So without fully thinking it through, there's these are things that have been tested with both lab experiments and also with computations. And these are then plugged in this dust opacity calculation. So here's a website, a GitHub, where one can put in, like, I want to have a grain size distribution with this minimum, this maximum, this slope between the different grain sizes, this kind of composition. And then I get a dust opacity table, so a kappa as function of wavelength or frequency that I can use to convert my emission to a mass, to a surface density. Okay, so I already mentioned like that all of this was valid, assuming that dust is optically thin, so that all of the dust is observed simultaneously. If it's not true, if the dust density is so high that it becomes optically thick, this is what's going to happen. So now we have our flux expression, or our specific intensity expression. If tau is larger than 1, so that means it's optically thick, that means that this term actually disappears. You understand? If this becomes large, then this whole thing becomes closer to 0, so the whole thing disappears. And then the specific intensity is only proportional to the time function. And that means that my flux density is now proportional only to mu squared, no longer mu squared kappa. And kappa was my surface density that we needed to calculate the mass. So you can imagine the flux is no longer depending now on surface density or mass. And also alpha, the observable quantity, is no longer proportional to the dust opacity coefficient. So alpha no longer represents the dust opacity. It will just be equal to 2, meaning that it's optically thick. So if you want to check if your emission is optically thick or thin, you can only do this if your emission is spatially resolved. If you have a good measure of the temperature at that location, and the emission itself is sufficiently spatially resolved. So what you can do is essentially to convert your flux, like to revert this equation to temperature being a function of flux. That is called the brightness temperature. And I compare that with the physical temperature at that location. Because remember, if your dust is optically thick, your flux is equal, your flux is directly proportional to the local temperature. So if in the most extreme case, the brightness temperature will be exactly the same as the visible temperature. But if the brightness temperature is well below the physical temperature, then you are not optically thick. So again, this is mostly if you want to do this kind of calculations eventually. Okay, so I already mentioned that the spectral slope is something that people are using to estimate whether grains are growing, what the typical grain sizes are. And that's based on all these assumptions of villaging and optically emission. And so these are some typical values of that spectral index. We see this plot here, the number of data points. We see that most of these values are kind of between 2 and 3. We know that for the interstellar medium, there are only small grains. There are no millimeter grains whatsoever. The spectral slope there is 3.7. For values between 2 and 3, we generally say, oh, there must be millimeter grains present. You get, because that means you have a beta between 0 and 1, that is consistent with millimeter grains. But of course, you could also be partially optically thick. If your spectral index is 2 or even lower than that, you're definitely optically thick. If you're much lower, you're actually talking about non-thermal emission, which so that originates from the star. That's no longer related to this. It all sounds very vague, but unfortunately, most papers, most studies are also kind of hand-wavy about this. So you calculate the spectral index, you say, oh, it's this number, so there is probably grain growth, or it is optically thick. And the reason is that we simply don't know for sure unless we can really calculate this dust opacity directly. I hope, even if you don't fully understand it now, I hope I've given you some of the tools that are behind this reasoning, that are behind these calculations, so that you somewhat understand how this emission is generated. Don't worry, because it took me a long time to really think through this as well. So I'm really not expecting anyone to grasp this fully. Just want to give you some idea of where it goes. Okay, so I mentioned a lot about the spectral slope alpha that you can calculate from 2 wavelengths. So you can just say what is the slope between 2 flux points. But if you have 3 or even more wavelengths, you may remember this from a statistics course. If you have enough free parameters, you can also, if you have enough data points, you can also derive more free parameters. So 3 or more means that you can fit the opacity, temperature, and surface density, so essentially optical depth, together. And in that way, we can get better constraints on our basis composition. So this is something that you will see also quite a bit in these multi-wavelength studies, where they're able to measure, to essentially fit the temperature, the surface density, and, well, the dust opacity. In this case, they've already done a step further there, the maximum grain size, all in one go. And
What kind of wavelengths do we use to calculate these units?
So this is all in the millimeter regime, right? And in this case, they use 0.9, 1.3, 2, and 3 millimeter. So in this case, even if the emission is partially or fully optically thick, you can, because you have multiple wavelengths, you can still derive the surface density to some extent.
Is that already used by looking at infrared provided
no, because in the infrared, the Rayleigh-Jeans approximation is not valid. So then you cannot make the calculation. So it all again relies on that approximation. a really good question. Okay, so now you have some idea where these dust masses come from. So let's now take a look at what the observations tell us about the dust masses in nearby clusters. And I've already mentioned a few times that we've been doing these snapshot surveys with ALMA, so low resolution imaging of all the disks in nearby star forming regions. That results in these nice galleries of dust continuum images that are mostly unresolved. But the good thing about these surveys is that at least we have good measurements now of the continuum flux, the flux, the insulated flux that we can convert to a dust mass using that equation. And with so many disks, we can now look at the statistics of disk dust mass as in the context of evolution. Because we know that these clusters all have slightly different ages. And what we see in the cluster, and I also showed this yesterday in the dust evolution lecture, that the dust mass overall decreases with age. So the younger clusters have typically higher dust masses than the older clusters. Yeah, this, of course, this still relies on the assumption that we understand the dust capacity that the emission is thin. There's also some debate there, but this is sort of our general view now of how the dust mass evolves. We can go even a step further back to the class 0 and class 1 disks. I already showed that in the beginning in the comparison with the exoplanets. So now we have again this dust mass distribution, including class 0 and class 1 disks, so the embedded disks. And what we see is that the dust masses there are even 1 or 2 orders of magnitude higher. And they also did a comparison here where they used 9 millimeter data, which is more optically thin than the 1.3 millimeter data. So this is, and as you can see, this is mostly relevant for the class 2 disks. So the class 2 disks are definitely more optically thick at 1 millimeter than at 9 millimeter. And that's, that means that if our disk dust mass drops, it cannot be just an opacity change, it cannot be a change of the grain size properties. It's really the physical mass that changes. Another thing that we can look at for disk dust mass evolution is the correlation with the stellar mass. So here we are again looking at multiple clusters. We see the dust mass as a function of stellar mass. So we see a whole bunch of data points. Also here you kind of have to believe the statistics here. This is a correlation, but the correlation is statistically significant. This is particularly driven by all of these upper limits here. So all the triangles, they are upper limits, and those are taken into account when calculating that correlation. So there is a correlation between dust mass and stellar mass. Higher mass stars have higher mass dust disks, and also that dust mass decreases over time, what we were seeing before, but that is mostly for the lowest mass stars. So the decrease of dust mass is the strongest for the lowest mass stars. But then there is a bit of an exception to that. If you split up targets by, the ones that we know the transition disks or ring disks, so TDs and structures, if we plot those separately from the main clusters, what we see then is that their slope is a lot flatter, and clearly that there's no dropping of the dust mass. And this phenomenon, if you recall, we have these two options of dust evolution. It may be related to this idea that the bulk of the disks are affected by radial drift, so their dust mass drops over time. But some disks that have dust traps, for example, the transition disks, maintain their dust mass over time. And but another effect here is actually that the drift velocity is more efficient around low mass stars. okay?
Yeah.
Is that the radial drift itself is more efficient around low mass stars. And this is essentially because the drift velocity, if you go through all the math, is proportional to the fourth root of the stellar luminosity, but only the square root of the stellar mass. Obviously, both of these are lower for lower mass stars, but the mass term is more dominant. So that's how the drift velocity becomes higher for lower mass stars. And you can see that here in this plot, the drift velocity for a 0.1 solar mass star versus a 1 solar mass star. Again, as function of age. And this was again work by Paula Pinilla, of course, in the dust evolution modeling. And she actually took that a step further by doing a whole sort of population synthesis, where she looked at these, again, these unperturbed densities, so the disks without pressure bumps. The lines are the data, the dots are the models. It's usually the other way around. In this case, she chose to plot it this way. And also, what she tries to show here is that the dust mass at every stellar mass drops in the drift phase, but in the case of dust trap, the slope is even, like the drop is only present for the lowest mass stars. And the reason for that is actually that the dust mass in dust traps around low mass stars, because they're more affected by radial drift, they also grow more efficiently to boulders. So that means that their millimeter dust mass becomes lower. So essentially, what she concluded here is that we still don't fully understand what's happening here in this in these trends. It's like the black curve being the transition disks, and these yellow the colored curves being like regular disks. It's still not entirely clear like what is drift and what is trap and what is happening with the dust mass in both of these cases. So I recently did another calculation of this slope of the transition disk because I discovered a bunch of transition disks that were a lot fainter than the ones we knew before. For example, this one. It's a very faint dust rain. The inner disk actually becomes really bright, and that means that now we have again the dust mass for the stellar mass, the transition disk slope, and I haven't drawn it on the plot because it makes it very, very hard to read, but that slope is actually similar to the one of the photoplanetary disk. So maybe that is related to the fact that in all of these cases, you still get a pretty strong slope that is actually consistent if you look at the data properly. Okay. So another aspect of this mass evolution, this is also something I showed yesterday. I hope you don't mind that I'm repeating things because I feel like some parts are like both theoretical and observational important. We've seen that there is this strong drop of the dust masses between protoplanetary disks and debris disks. And back then we thought this was some kind of sign of rapid disk dissipation. But I've been proposing that this may be something else, which is that the transition disks are mostly found about higher mass stars. The debris disks are mostly found about higher mass stars. So this drop in dust mass is only in this higher mass star region. And essentially the drop in dust mass is simply the growth to planetesimals in these large-scale dust rings that we are observing. Okay, then I think I just have a few more slides on completely different topics. So this is not so much dust mass related, but it's more like grain size related. And this has to do with polarization. Because with ALMA we can measure polarization in millimeter emission. Sorry, maybe let me ask first, do you guys know what polarized light is? It's like the direction, the two directions of the light, right? And so we can measure this with ALMA in a special setting. You cannot just do it afterwards after they have been taken. And that means that we now have measurements of the polarization angle in several of these disks in the container. And so the idea here was actually that you have two mechanisms that can change this polarization direction and also the intensity of the polarization. So the first one is self-scattering. So scattering of the dust grains on the cellular will always result in a polarization direction parallel to the minor axis. So the pattern will look like this. But then you also have intrinsic polarization of aligned dust grains in this, and that will look like a circle, like an azimuthal distribution. Now, the scattering efficiency is very dependent on grain size. And so essentially the efficiency of the polarization becomes high at a very specific grain size regime in a specific band. So what that means is that if you detect self-scattering in one band, but not in the others, then that means that that band can tell you directly what the grain sizes are. And so this is what, again, multi-wavelength observations have told us. This is for HR tau. We saw that the polarization angle is like parallel to the minor axis, so it's self-scattering in band 7, a little bit still in band 6, but really not anymore in band 3. And because self-scattering is visible in band 7 and no longer band 6 and 3, that means that the maximum grain size is only about 100 micron in these disks. And this is an issue because we've been saying, based on all these spectral index measurements, based on all these alpha measurements, that the grains are more like a millimeter in size, or an order of magnitude higher. And I was at a conference last year where both people made their case. So you had the spectral index, people using spectral index measurements, Annabel Sierra and Marco Tizzari on one hand, and Akinasa Kataoka, who has been doing all these polarization measurements. And I was asked to give the summary talk at the end, so I made a little graph out of it. This is still an ongoing debate. So we don't know why polarization gives us a different grain size, maximum grain size, than the spectral index measurements. To summarize, this dust mass is calculated using several simple assumptions, like optically thin and effective millimeter grains, and that we're in the radial genes regime. The dust mass changes in evolutionary plots can be interpreted in multiple ways, both tracking and drift. Multi-wavelength observation can help to disentangle some of these dust opacity effects, so we don't have to worry too much about the thickness anymore. And the maximum dust grain size, I just say, it remains unknown. Right now, we don't have a way to explain both at the same time. So, that's it about the dust mass. We can take a little break now, and then we move to the gas mass part of the lecture, unless there are any questions right now.
Everything is absolutely clear.
Perfect. Or everyone is balancing. Okay, let's take a break and coffee.
Hi. Personal question.
Yes. Okay.
So what would be the device
Yeah.
to update the data observations and material? But I have a question for you. There's someone or somewhere or well that's terrible because I am not here. Do you know something about this kind of this kind of animation? I mean, we inserted the profile of the PDF, and for example, the math system, or the, for example, mass, you know? So
Yeah.
I want to compare with them, not only the observations, but with theory. So I don't know if you can use the profile of the density distribution of the area, or I don't know, the total mass system.
Let's see. So, yeah, so like the study that I'll show you on the distribution for the discussion is done by 5 models who wrote this as a statistical tool that corrects. So, I don't think that code is public. You can reach out to them and say they're interested in using this.
Because well, I want to compare my results,
Yeah.
not just with
No,
observations.
that's really good. That's really good. So yeah, you're not actually, so you could not compare the observation, but with corrected observations, right? Yeah. So he has written that, and I think the best thing you can do is just well, maybe take a look at that paper. This is Mulder's et al. 2021 A. There's 2 papers. The first one.
Okay.
And so just read through it so you understand how this works.
Yeah,
I think
because
he also refers to the newspaper, like, it's just Fernandez. And then you can just send me the works too. But yeah, I'm sure he will be able to.
okay, because well, for example, I could just this is the profile that we construct after the analysis and
Yeah.
and this is the observation. So we can say, for example, for the center map, we can say that maybe there are more planets, and this is the center of mass, the possible center of mass, and this is the observation. So we can say that maybe future observations will discover other planets. That's one of the results.
He actually does something like that as well in this paper. So I didn't talk about that part. He also looks a little bit at the distribution of the surface space in physics compared with where so yeah, definitely read the paper.
Okay.
And then and see how it compares. So yeah, you should never be afraid to email astronomers, even if you've never met them. If you're interested in their work and want to make a comparison, of course you have to make sure that you've read the paper. You can say, hey, I saw this title, can you tell me more about it? Like, I wouldn't respond to something like that.
Okay.
But if it's like, oh, I read your paper, I'm interested in making a comparison, can we maybe collaborate on using the code? That is very, that's really useful. Really talk about it. Also, he can also then maybe look at the implications.
Okay, thanks. Yeah, because what that's the idea. Where with something.
Absolutely, absolutely. Yeah, okay.
Thanks
Oh,
so
that's
much.
no problem. Okay.
Remember? They are set in those,
They-
yes.
Are they saying my handwriting is bad? I don't really understand this. No, this is Eo's handwriting.
Yes.
So he copies no notes.
Well, they all need it.
Yeah. No, that's fine, Like, I want them to write on. I'll ask you. Sorry, I'll leave you on that.
Remember that I need your signature?
Yes. Yeah.
So it seems like what is receive the money.
Yeah, I never counted it, but
Wow, please. I want to steal money from you, trust me. And this is the 13th, 4th of December. End of December, this is this part.
I understand. I'm not selling my babies here. Again, I trust you.
Thank you very much. Can you just let me have a look at your passport?
Yes.
For a moment, I will take a picture because I cannot take a copy now. I'll take a picture of the stamp.
I have a scan in my email it to you.
For the stamp?
Oh, no, sorry, no, of course,
No, your passport, the front page, I have it.
I already sent it to you.
Yeah. No, I understand.
Well, sorry, you were on the street. He totally ripped me off. Saying, yeah, I don't have change. Whatever. I lost it.
Thank you very much.
Know about some classification of the solar systems? I mean, not just the planets, not just like cosmic, no, just like the system at all.
I've never seen it, but I'm not a total expert in exoplanets.
Because we know of one, much more into, but I didn't know it also I have something to compare. So,
No, I don't even know if we have enough statistics to really make that estimate. So, yeah, no, I can't say. I can't say.
don't worry, don't worry.
It would be, you could maybe ask Tess about that as well. Like all the populations that I know are, there are, there are Kepler planets, opposing Kepler planets, there are warm giants and cold giants, white dwarf giants. There are
Yeah, but that's those
and there are,
planets.
yeah, and then there's some studies. I'm actually going to show a little bit about that on Friday. On like a correlation between closing super Earths and cold giants. But then there are other studies that contradict that, so I'm not really convinced that the correlation is real. It's still pretty messy.
Okay, well, thanks. Don't worry about that.
Okay, can I ask your girl help here? I think one of you had this kind of necklace yesterday, and I bought it on the street this morning, but I can't open it. I hope it.
Yes, it's built like this.
Okay. Yeah, I don't want to break it. So they just made it little. Worst case, I keep it up. Can you call everyone back in?
It's not literally.
Oh, okay. Yeah. Let's talk about it. Anyone still here?
Yeah, there are two outside.
Yeah. Okay.
Leiden. So yeah, there are two outside and there is one outside.
Okay. Let's get started. Okay, so we talked a lot about the dust mass, and now we're going to talk about the gas mass of the disk. As I mentioned, it's a very fundamental property, but there are many uncertainties on the disk mass depending on the method that we will use. And so there's this famous example of a disk, Hydra, where they estimated the gas mass, and the different methods have resulted in more than two orders of magnitude of different values for the disk gas mass. So the main methods that I'm going to discuss today are, we can use the dust mass and multiply it by 100, because we know that that is the mass ratio in the medium, where everything is optically thin and simple. of course, this has the issue that we know that the dust doesn't follow the gas. Therefore, we don't think that the ISM ratio is really representative. And finally, we have all of these issues with the accuracy of the dust mass. So if we're underestimating dust mass to begin with, then we're sort of accelerating that by deriving gases. We can use CO AstroTwinCoLOs because I've mentioned before that CO is the second most abundant molecule after H2. H2 itself cannot be used because of lack of dipole moment. So we'll essentially go through that method quite a bit. There we have issues with the CO being optically thick, that we don't know for sure what is the ratio between the CO and the H2. It's again different than ISM. And then finally we see effects of depletion, which I know is so this in a second, that the CO abundance changes with time. Then we can also use HD measurements, so this is deuterated molecular hydrogen. It's still hydrogen, but the other isotope. And the problem with using that measurement is that you can only measure it in far infrared, which is inaccessible from the ground. So we've only done it for a handful of disks with Virtual. And at the moment, there's no other far infrared mission for that. And another issue is that it depends a lot on the vertical structure, the temperature structure that you assume for your disk. And finally, there's self-gravity. I'll come back to that at the end. You need very good kinematic data. So let's start with the CO. So we essentially using molecules in order to measure gas mass. Remember that if we want to use molecular line emission as a tracer of mass, we need to really understand the density and temperature structure in this. And we know that there are these large gradients. We know that the dust temperature drops radially, but also it actually increases vertically. The temperatures are higher on the surface, and the gas temperature is even higher because there are additional heating mechanisms with gas. And the density is highest in the midplane and becomes smaller further out, and also radially it decreases. So these are the density we can parameterize, the temperature we can either parameterize or calculate with radiative transfer, but it always relies on a lot of assumptions. So these are just things we need to think about when we're using molecular lines. So if we look at the gas disk from the side, we actually have additional issues when looking at using molecules. That is that not all molecules are in gas form throughout the disk. So in the surface layers, molecules will be photon associated. So for example, CO will just fall apart into carbon and oxygen. In the midplane, a little bit further from the host star, the temperatures are so low and the density is high enough that molecules are frozen onto the dust ring, so you get CO ice there. And only in this region in between, molecules CO will be present in the gas phase where they emit radiation that we can measure with on. So I already talked about the story of H2 versus CO. So CO is second in abundance with respect to hydrogen. The chemistry, at least the chemistry itself is really well studied, so we do understand chemical networks. I'm going to talk a bit more about that this afternoon. It seems like the most perfect molecule to derive gas surface densities. So you may remember this from an earlier lecture where we talked about line excitation. How do molecules emit light? So you remember that I told you molecules move around randomly and collide with each other, going to excited states and then emit photons that result into a spectrum. So what sets the strength of an emission line based on this mechanism? What are the properties of the gas that make a line stronger? Temperature, exactly. And also?
Pressure, density.
Density. exactly. So it's the combination of density and temperature that sets the line strength. Of course, that makes it more complicated because if you have a stronger line, you don't know which one of the two has increased. So that's why you always have to either calculate the temperature or assume some temperature in order to do that conversion. Okay, so we can, sorry, I don't understand this slide. I'm confused. I don't know this slide, sorry. So we have, so the CO molecules are typically located in these layers of this. So I already mentioned there's this photon association layer here, the icing plane here, you can see it on the right. And so most of the CO molecules is highest in this region. The HD, which we can also use, comes from a little bit higher layer. So that's why it is more sensitive to the assumed temperature structure, because of this vertical temperature gradient. Then a problem with 12CO is that it's optically thick. So whatever you're measuring, the emission itself comes from this layer in the top part of the CO column. Remember, we're looking from the top, right? So we're looking from the top, measuring emission, but we're only going to measure the emission from the top. So that's why we like to use CO isotopelogues. This is, for example, 13CO or C18O, but we can even go C17O or 13C18O or 13C17O. All of those have been detected in this, but they are increasingly less common. So that means that they're more optically thin, but also fainter, so they become more harder and harder to detect. So the good thing about 13CO C18O is that their emitting layer comes from much deeper in this, usually as far below as here. So just to kind of summarize that in one picture, the 12CO emission layer, the thallium layer, is located generally up here. C18O is usually down here. And so the abundance ratios are listed over here. So 13CO is 68 times less common than 12CO. C18O is 560 times less common than 12CO. So there being a lot less of it, which makes it more appropriate for measuring gases. Okay, so say that we have molecular light emission from CO isotopelogues, and we want to interpret that. I already mentioned that we have to make a model of this with a given density and temperature structure. And so this was the first time this was done was by Williams and Nest in 2014. They didn't do chemistry, they just did a parameterized model where they said, well, there's this molecular layer here. This is where CO over H2 is set to 10 to minus 4, so the ISM ratio. And then outside of that regime, the CO level is set to 0 because of photon association and freeze out. And then also the temperature was just parameterized throughout the disk, wasn't measured. And in that way, you can essentially run a grid of models for different stars, different disk masses, different vertical structures. And for all of those, you calculate the expected 13CO and C18O emissions of each of these models. And then you plot that in over the plot. So this is the C18O, integrated C18O emission, integrated 13CO emission. All the colored points are models. So the large bit of models we calculated for different disk masses, and so the different colors represent different disk masses. So you cannot do like very fine sampling of the disk mass. You just say, well, it's 10 to minus 4 or 3 times higher or 10 to minus 3, so it's kind of factors of 3 every time. So and then the reason that you get different functions is because of all these other assumptions about the structure of the disk. And then they took data for a number of disks, so these are the black data points, and they put that on top of this plot. So so this way you can say, well, if I measure this combination of C18O and 13CO, that means I'm in this mass regime. So this must be more or less my gas disk mass. And so these are the results that they found. On the top, and sorry for the font sizes, on the top is the gas mass, and this is just all the different sources, like just as functional source. And this is the MMSN, the minimum mass solar nebula. So most of the gas masses that they derived for these disks are well below the minimum mass solar nebula. And then the second measurement that they did was the gas to dust ratio. So they also calculated the dust gas using the method that we discussed earlier today. And you calculate the gas mass, you divide the two numbers on top of each other. They find that most of these disks had a gas to dust ratio of only 10. So well below the ISM ratio of 100. So that was weird. But maybe there was an issue here with the sample that was chosen. Because there's a number of sources that were observable with the SMAs from before ALMA. So let's now do the same thing, but then for the Lucas ALMA survey. So also there we had all these continuum detections, but we also had detected 13CO and C18O. So these are blobs of 13CO, C18O integrated emission. Again, comparing the integrated fluxes, all these data points, with the grid of models, and we saw the same thing. So now on the top we see the dust masses, so it's sorted by all the sources, sorted by dust mass, okay? Gas masses are listed over here. Again, all of them are well below the minimum mass solar nebula, and all the gas to dust, and the gas to dust ratio, so some are indeed close to 100, but many of them are closer to 10. So, and this is a complete disk survey, so this is no longer a selection effect of the brightest disk. It seems to be beating something uniform for many of the protoplanetary disks. Now, the way that this was interpreted, so that we have these very low gas to dust ratios and gas masses. There are actually two options, and that was already discussed back then. Maybe the gas is already dissipated in this. Like maybe there's simply more gas accreted and the dust mass kind of stays around. Or maybe something is happening with the CO. So maybe essentially the CO is depleted. Maybe we do need like a proper chemistry calculation of the CO bundles in the disk rather than this simple parameterization.
What could be the chances of that happening in all the planetary disks that we observe?
Sorry, which one?
What would be the chances of the CO already being depleted?
Well, I'm going to discuss that now. So
Alright.
yeah, no worries. So it's essentially so the idea was that okay, something is happening with the CO. Maybe chemical reactions are already converting the CO to other molecules, and we don't see that in our simple parameterized disk model, but we should be able to figure that out. So in order to do it, we can use this code called DALI, that's developed by Simon Ruderer. And this model, essentially you give it a density structure and a standard spectrum to have a radiation field. First, we calculate the dust temperatures throughout the disk as a starting point, and then you do an iteration between chemistry, thermal balance, and excitation level. So chemistry is essentially a chemical network, so all the chemical reactions of simple molecules that we know. Thermal balance is essentially the heating, everything that heats and cools the molecules depending on the local conditions. And then finally the excitation level. So whenever molecules get lifted to a higher excited state, emit a photon, those photons may again heat their surroundings, etc. So you can imagine that these processes all impact each other. So you need to do this in an iterative way. So in every location of the disk, you need to run calculations many times until it converges. But finally, when it's done, 8 hours later, you are, yeah, I've done this modeling for my PhD a lot, it was a pain.
Only 8 hours.
One model, 8 hours. Yeah. So in the end, you're left with essentially an abundance structure and a gas temperature structure that is consistent with chemistry and physical processes. And then with that, we can again ray trace molecular lines. We can calculate how molecular lines look like based on the given density structure. And it includes obviously things like the freeze out, the photon dissociation, etc. So this is supposed to be more accurate than that parameterized approach. So these are some examples of the abundance, molecular abundance that we get in these disks. So for the CO, well, it looks kind of similar to what we had before, right? We had this molecular layer here, and then no CO here, photon dissociation, no CO here, freeze out. And actually in the red layer, the typical value is like 10 to the minus 4. And if we go to the CO isotopologues, the 13 CO, C18O, C17O, all the abundances go down. So you see here, the red is like 10 to the minus 7, 10 to the minus 8. So it's not, like, it doesn't look very surprising. It kind of looked how we had expected, even though it took us 8 hours to calculate. And one particular thing that was considered here that was definitely new is something called isotope selective photon dissociation. I challenge you to repeat that 20 times. So what this means is that the photon dissociation, so the disruptance of molecules, is different for each isotopologue. So that means that the layer where C18O is photon dissociated goes further down than the 12CO. So this is, it's again, just a little bit more advanced calculation of what the abundances are going to be. So also for these models, Nienke et al. Calculated a grid of disk masses using the exact same approach, 13CO, C18O, colors represent different models, different disk masses. Okay, let's overplot those lupus data points in this grid. And unfortunately, the same thing happened again. So essentially, the gas masses were pretty well estimated by that parametric model. We didn't need to do all these super complicated stuff. Gas masses are low, gas to dust ratios are low. Now, I already mentioned, so at least this part of the CO chemistry we understand well enough. So then there was this alternative alternative explanation, that is the gas dissipation. Maybe the gas in the disk has already been mostly, critical to start, the disk is already starting to evaporate. But that doesn't really make sense either, because if we look at the accretion rates in lupus disks, they are kind of typical for an expected, for a gas disk at a few million years. So essentially these disks are really in the middle of their lifetime. They're not dissipating yet. So something else must be happening with the CO. Like we're missing something in our CO chemistry. Well, I'm going to come back to that. But let's first verify that there really is a problem with the gas concentration by looking at these HD measurements. So the HD is like an isotopologue of H2. The ratio is about 3 times 10 to minus 5, so 300,000 times less common. And this was the first HD detection in a protoplanetary disk. Again, see the Brahydra, this very bright famous disk. So they measured the line, calculated the line strength, ran again a thermochemical model to calculate the temperature, density structure, and found that the disk mass here was consistent with 0.05 solar masses, so somewhat just a little bit above the minimum mass solar nebula, and a gas to dust ratio that was about 100 or even higher. But that is for this one disk, right? So if we now compare that with what was estimated from the CO. So gas mass, I don't have a plot of that because it's, well, it's an older paper. But the gas mass derived from C18 emission for this particular disk was only 0.005 solar masses. So that means that there is some additional chemistry that depletes the CO by at least a factor 10, assuming that the HD measurement is correct. But I already mentioned the HD was measured for a few more disks. In fact, it was observed for 6 more disks and only 2 more detections, unfortunately. This one, DM tau and GM Marel. The significance of this detection was not very high either, like 4 or 5 sigma. But okay, we believe it's a lot. Say so. And so also for these disks, they estimated the gas mass. They found kind of 0.05, 0.2, or essentially gas to dust ratios of 35 to 140. So on average, it's still pretty close to the ISM. It's a lot higher than 10 that we found for CO measurements. Well, there is, as I mentioned, this dependence on the assumed temperature structures. This was shown also by a later paper, that for a disk mass, for a given disk mass, the HD flux will be quite different if you assume a higher temperature than a lower temperature, essentially, depending on where the HD emission is emitted, so the vertical structure. That, yeah, this is so there is some uncertainty there, but let's assume for now that the HD measurement is more or less accurate. That means that their CO measurement is not. And yeah, just to remind you, so why are there no other HD measurements? This paper of 2016. So those are the last HD measurements. Why haven't we done other disks? What do you think? So what wavelength is this?
I was not asked that.
Okay, sorry. Yeah, it's far infrared.
Okay. So there's no vision covering that.
Exactly. Yeah. So these measurements were done with Herschel, which was well, ended its mission in 2013, I think. And that means that, so after that, there has been no other far infrared mission that was sensitive enough. The only exception to that is Sophia, the plane that was doing far infrared. But of course, that plane, the telescope that fit in that plane was fairly small. They were not sensitive enough to measure the HD value, so it was not an option. And also right now, there's no plan last year, I think, or 2 years ago. So yeah, there's unfortunately no plan in the near future. Okay, so we don't have more HD measurements, but like I said, if we assume that the measurements so far are correct, then we really have an issue with the CO. And remember that the HD measurements also indicated that this ISM ratio of 100 was reasonable, right? So now we're going to go from that assumption, we're going to calculate how much the CO needs to be depleted in a larger sample of disks. So it's a bit of a loop reasoning that I will show you soon that this actually makes sense. So if we start from the assumption that the gas mass is 100 times the dust mass, we can derive the CO depletion with respect to 10 to minus 4. So this is done by, for example, Coco. So she derives the intensity profiles of the integrated 13CO and C18O. So we have the 13CO C18O flux, and based on that we can calculate an abundance. So this was done using, again, thermochemical model, given this dust mass times 100 as our total disk mass, and then calculate what is the CO abundance, the expected CO abundance for that particular disk. assuming this ISM ratio 10 to minus 4. And then we're going to see how much do we need to change that 10 to minus 4 in order to reproduce the data. So, as it turned out, they had to vary this the level of depletion by factor of about 10. So these are the different levels of depletion of CO to reproduce the data here in blue. So it's the integrated intensity as function of radius, and as you can see, the sort of solid / dashed dotted seems to be most consistent. So that's depletion about factor 10. Over here we have to go for a factor 100. So it depends a little bit on the disk, but we kind of find the same conclusion here, that you need a depletion level. So here we actually see the depletion level itself as a function of radius derived from these C18 observations. So for these 4 disks, we see depletion levels varying from, like, for Hydra about 100, for DM tau it's about 10, maybe actually going up to 1, so in that case there's no depletion. So it depends a bit on the disk. And so what's interesting is that in this particular disk, something is happening around the CO snow line. So the depletion there's no depletion over here. Like the CO depletion factor is about 1. And over here it goes down to, goes up to 10. And this happens to be around the CO snow line. So remind me, how do we know where the CO snow line is?
We know the spectral type of the star, and we can characterize how it irradiates the disk.
Yeah.
So what temperatures it have, function of radius.
Exactly. We can calculate what the temperature is in different parts of the disk. We can see where the temperature drops below the CO freeze out temperature. Okay, so then in a follow-up study, they looked at this a little bit more carefully with even more CO isotopes, so not just C18O, but also C17O and 13C18O. And they found the same thing. They found that, you have this strong depletion outside the CO snow line, not inside the CO snow line. Can you think why this is?
I guess it's because of the state of the CO. You have. Oh, that's counterintuitive.
So remember that the emitting layer of the CO is higher up in the disk, right? So even though CO snow line is located there, like outside that CO is frozen out, but this is only in the midplane. But the molecular layer is above that. So how come that the CO in the molecular layer is depleted as well? That's really the big question. It's okay. I just wanted to give you the answer. So this is the hypothesis. If the CO snow line is located here in the disk, that means that outside CO snow line in the midplane, we have grains with CO ice. And in the surface, we have CO gas, that's red. Those grains will grow, settle, and drift inwards. And they will continue to do that. So essentially, they are taking away CO gas from the outer disk into the midplane, like even higher up, whatever CO is still is the gas is there. Everything that as soon as it gets locked up in the ice, it will settle and drift inwards. So you're really depleting the outer disk molecular gas from CO.
So it's like they're clustering the disk plane.
These are, remember, this is the dust evolution that we discussed yesterday, right? Like but what is so interesting is that this chemist usually didn't really care about dust evolution. They always thought, oh, that doesn't really concern us, but it definitely has an effect here because it's actually removing molecular CO significantly. But this is more, so maybe this first paper, this was just like an idea, an hypothesis. It wasn't really quantified. But in later models, they show that this can really lead to very high depletions. And so what's interesting in terms of the observations, so we have this CO depletion of like 10 to minus 5, 10 to minus 6, kind of the measurements that I was showing you before. That's for the class 2 disks. If we do the same measurements, same approach for class 1 disks that are only 1 million years old, there is actually no CO depletion at all. So whatever is depleting the CO is doing that in about 1 million years. And hey, that's about the time scale of dust evolution and the radial drift. That's perfect, right? This can really explain what's happening. And so there's papers by Leiden et al. Where they do this very extensive modeling, how much CO really gets removed from the outer disk over several million years. And so you see here, this is looking at the disk model from the side, vertical height, radius. At the initial point, 0.2 million years, you have the CO ratio of about 10 to minus 4. 1 million years it starts to go down. 3 million years it's really depleted by about 2 orders of magnitude. And in this plot, he's kind of summarizing when drift is present. So this is the black model. There's a lot of information in this plot, so I'm just going to talk you through it, but I need to think for a moment. Yeah, so he also considered the influence of cosmic ray, like if you have more or less cosmic ray ionization. So that's the gray and the red. And then he considered the CO abundance as a function of time, so like following the curve inside the CO snow line and outside the CO snow line. So the main model, the black one, you can see that the CO abundance drops by about 1.5 order of magnitude outside the snow line, and inside the snow line it stays things vary a little bit, but it stays more or less the same. And so he does the comparison here with, he called this the DR models. These are this is reduced drift reduced, that's what DR stands for. So this essentially means if there's no drift, you have dust traps. If drift is reduced, you will essentially also deplete the CO, but then for the same amount of dust mass. So you essentially get a slightly bigger. So the whole conclusion of this work is that CO depletion can be explained by dust evolution. This is just something we need to start taking into account in our CO chemistry models. And that hasn't been done so far. Yes?
My question is because the article I chose is kind of related to this.
Yeah.
Is the effect that stars that are emitting X-rays, and how does it affect these type of things? But of course, it's not CO, it's another one.
Yeah, it's CO plus.
Yes.
Yeah.
But is it common to also consider that type of radiation, not only like cosmic rays, but also like
Yes.
taking into account?
Yeah, so X-rays and cosmic rays are, that's indeed, sorry, I haven't really talked about that much. The radiation field from the star, there is the UV, the thermal light, but there's also X-ray and cosmic ray, interstellar cosmic ray. These radiation fields are not really known for most disks and for most environments, so we just kind of pick a value, but we know that the choice of that value, the assumption of that value, is going to have an effect on the chemistry. So essentially, we sometimes use chemistry, like observational molecules, to constrain the X-ray rates or the cosmic ray rates. Yeah. So this is the way to think about it. These are not things we can measure directly, but we can measure the effect of the chemistry and then sort of backtrace that.
I was thinking about,
Yes.
maybe I'm here changing hypothesis.
No.
Like, when you got this CO depletion to
Uh-huh.
this, as it solidifies, it increases the calorific index, capacity.
Yes.
So it lowers the temperature of the disk. And couldn't it be affecting the disk evolution in manners that we haven't encountered?
Yes. So I'm pretty sure that in these models, the temperature is also being affected, but I haven't seen all evidence for it. It's possible. Yeah.
So like lowering the temperature of the disk may shrink the disk.
Yeah, at least the part that we can observe. Yeah. Yeah. Lowering the temperature would mean that the emission would go down. So yeah, that's a good point. I don't know if anyone has done that. Yeah. To see how significant that is. Yeah.
That's it.
Yeah. No, that's a really that would be a fun project for sure. Okay. So I'm all excited about this CO depletion solution. So the current data suggests that this isotable scenario can explain the high CO depletion under the assumption that we have gas-to-gas ratios of the ISM preserved, so that it is about 100, which seems to be the case for this that have been studied in HD. The problem is that these models that I was showing you are essentially just assuming a drift all the way in. So then CO ice get transported inwards, and eventually it goes inside the CO snowline where it evaporates again. So you just get a redistribution of the CO. However, most of the disks where they've been studying the CO depletion were disks that had dust traps. So it's actually, you're not actually looking at the same physical realm. Like things get transported inwards, like you still transport from like 400 AU down to maybe 50 AU. But your dust, a lot of your CO ice from the outer disk remains frozen out because it gets trapped at that outer dust trap. Nobody has actually done that yet. Like what really happens with the CO abundance inside the snowline if the CO icing pebbles are trapped there. Yeah, so this is also still something that kind of needs to be done. And there's a second issue, and that is if you assume, if you start from this assumption that the gas mass is just a dust mass times 100, you assume that your dust mass represents the total amount of mass. But what is how accurate is the dust mass in a disk that is drift dominated, where all the dust is drifted inwards?
Yeah, you don't accumulate dust much, I guess, because you don't have the dust trap.
Yeah, well, the thing is actually that your dust mass is all drifted inwards and even lost onto the star.
Yeah.
So what you're measuring is not the initial amount of dust. And also that is not, yeah, it has to be, it is okay to make that assumption if the dust gets trapped, then your dust mass in the traps is kind of the same as the initial dust mass of your disk. But if you are a few million years in, and you would be looking at a disk that is where there are no dust traps, your dust mass is probably underestimated. So then, yeah. So these are just things to kind of think about. So this is kind of repeating my point. The dust mass drops very quickly. The observable dust mass drops very quickly in a drift-dominated disk compared to this dust. And yeah, so this is a problem of bias in ALMA studies, also ALMA chemistry studies towards brighter disks, which usually contain dust traps. There's this weird misconception that all disks behave like with all this simply scale down. If in fact only the brightest disk have dust traps and the fainter disk do not. Yeah.
I also wanted to ask, are in the simulations for the model, do you find that the dust traps are stable with time? I don't remember. Do you find that the dust traps are stable with time? I don't remember you mentioned it. But is it expected to last for this year term?
Yeah, so the dust trap essentially remains as long as the planet remains. We can debate about that because the planet may migrate. We don't know. That's they haven't actually done a simulation because this becomes complicated. A planet disk interaction requires a hydro simulation, and it's really hard to do dust evolution in a hydro simulation. So we don't really know what happens if the planet migrates. Then if the dust just follows along, or if maybe it grows so far that it stays behind. This is still.
By the way, on a side note,
Yeah.
how do you compute this kind of interaction between particles in a disk of trillions of these particles?
In dust evolution, you mean?
Yes.
Trying to remember so I don't do these calculations. I think they do. So they don't do like individual particles. They do the dust density and the weight size distribution.
Like parcels.
Parcels, yeah. Make sure you work with parcels. If you want to know for sure, you would have to go to some of these dust evolution papers. But yeah, I just know it's not like a million particles. It's boxes. Yeah. Okay. Final point, and I'm not going to go into detail about this because this has only been done for one disk. There was this proposed idea that the velocity field in a disk is not dominated by gravity, gravity from the start, but also by self-gravity of the disk. And the proposition is that we can measure that by looking at the kinematics of the disk. I really don't fully understand this, so yeah, you can ask me questions, but I probably don't know. So what they claim is that based on the measured data points here, seen very scattered to me, that they fit better with self-gravity model, back model, than with a single Keplerian model. And self-gravity model is highly dependent on the disk mass. So essentially the disk mass is derived from this discrepancy, like the deviation from a Keplerian model. They've done it for one disk. I'm sure they're going to try to do it for more. It looks hard. That's the only thing I want to say about it. Okay, summary. So, determining disk gas mass has been a long-standing issue in quantum disk studies, and we are not there. The gas-to-dust ratio of ISM may be true, at least for some of the disks. 8D measurements appear to be the most accurate. They do depend on the assumed temperature structure. We cannot observe any more disks. CO isotopes definitely underestimate the gas masses. But maybe we can solve this if we account for CO depletion by icy double drift. We start doing this properly. So that's it. That's what I have for the gas disk masses. Are there any other questions?
I wanted to ask something about the CO isotopes. It seemed like the distribution in the disk was related maybe to molecular mass. Is that true? It seemed like heavier molecules were settling closer to the plane, like C18 or better.
No, so this is not settling. This is just the region where they are emitting. So and the fact that they get photo dissociated further down, so it looks like So it's not so much that they're lower; it's just that there is less of it in the higher layers. But who knows? Maybe freeze out is isotopologue dependent. That would essentially be making it essentially dependent. But I don't think anyone has calculated that.
Wait, and do that like just laying apart some quantum effects, particle effects.
Yeah, but it would be computationally impossible. Yeah, not with current supercomputers. Maybe someday in the future.
And today, those calculations are done with Python.
Yeah, so the parcel that's going to push can be done quite a bit. That's going to be done on memory. That's relatively fast. Yeah, so it's obviously that would have been an alternative for project this week. But yeah, since I'm much more an expert on observations, I didn't really want to give you guys the tool of figure it out. I'm not enough of an expert on this definition. Again, the software is online, there is a lot of documentation, so if it's something you're interested in, it's certainly something you can do, and that's everyone is encouraged to actually download software designed for all people. Okay. If not, so the plan for today, the rest of today, there's going to be one more lecture on chemistry and kinematics after lunch. I'm going to try to keep that one a little bit shorter. I'll probably fail, but I'll try. And for the rest of the day is meant for your project. So either preparing your paper presentation for Friday or work on your online-based production project. I want to remind you that the paper presentations are going to be the first thing we do on Friday morning. So we're not going to start the lecture, we'll do first your presentations. I'm going to make the schedule probably in the next hour. Just want to ask, and I'll put it on the screen, just ask if everyone's okay with that. And so the schedule is I'm going to divide the papers a little bit by topic, so that we first do everything that is related to dust masses, then to the kinematics, sort of things are a little bit logically grouped. I also send it by email, and then so just so that you know what to expect. Obviously, please be all present at all presentations, because we all want to learn more about what we'll be reading. And then after your presentations, I'm going to give another short talk about exoplanets. And again, the rest of the day we will work on all my projects, and by the end we will do a quick show some of the images that you produce, some of the results. Remember that the Algorithm Regression project is really free format, just to see how far you get. Ask me questions if you get stuck, we'll just see how it goes.
What time do we come to?
Sorry, what time?
What time do we come back here?
Now. Well, essentially after lunch, so what are we? 12:45? Sorry, let me check this. 13:45. Sorry. And on Friday, are we changing location?
Yes, I haven't announced that yet.
Okay, so remember, on Friday we're actually going to be on campus. So just everyone try to be on time and be at the right location. Right.